Let's talk about how an object will get charge now. So we've talked about charge, and we've established that a positively charged object is an object that has more protons than electrons, and negative has more electrons than protons. But how exactly does an object get more electrons than protons, or how does it get more protons than electrons? How do we charge an object? Well, there's two ways, two main categories of charging. One's called charging by conduction, one's called charging by induction. When we charge by conduction, we transfer charge. In fact, charging by conduction always involves a charge transfer, always. We're transferring negatives from one object to another, whereas induction never involves a charge transfer. Now, you might be asking yourself right now when you hear that, it never involves a charge transfer. How can we charge an object if we're not transferring charge from something to something else? Just trust me for now. We'll get to that shortly. It never involves a charge transfer. Now, conduction, usually, although not always, it usually involves touching. When you walk across the carpet and build up charge, you're building up charge in your body because your feet are touching the carpet. You're transferring charge from the carpet to you. When you touch somebody, you're transferring charge again from you to them. You're touching them. But charges can transfer without touching. If two objects get close enough together, sometimes electrons will actually jump the gap. They'll arc from one object to the other. That happens, believe it or not, even when you shock somebody with your finger. Every once in a while, if the potential difference on you, the charge buildup on you is strong enough, you can walk up to somebody and you can actually shock them when your finger is, 2 or 3 millimeters away from their body. They don't actually have to physically touch. It's like they're touching. They're close enough where the charges will just move from one to the other, but they don't actually have to physically be touching. Okay, it always involves a charge transfer. It usually involves touching. Induction never involves a charge transfer and never involves touching. So, if you've charged an object and the two objects touched each other, then it must have been conduction. If you've charged an object and there wasn't a charge transfer, then it must have been induction. If you've charged an object and they didn't touch each other, what do you know about that? Well, if they didn't touch each other, it could have been induction, but it could still have been conduction. We don't know for sure. It's inconclusive there without further information. Now, we can break each of these into two subcategories. Conduction can be broken into charging by friction and then charging by contact. Charging by contact, sometimes we just name it conduction. Sometimes we just call it its parent category, conduction. When you're charging by friction, you're rubbing two objects together. Charging by rubbing. When you rub that balloon against your hair and then put the balloon up against the wall, you've charged the balloon by conduction, more specifically by friction. When you rub that balloon against your hair, the kinetic energy of that balloon liberates electrons from either the balloon or your hair, transfers from one to the other. They were touching, charge was transferred, they were rubbing, charging by friction, subcategory of charging by conduction. When you walked across the carpet and you touched somebody and the charges tried to balance between you and the other person, that was charging by contact, subcategory of charging by conduction. So rubbing is charging by friction. We're going to say touching, although we're going to put that in quotation marks because you know that they don't actually have to touch. They can be close enough where it's like they're touching, and the electrons will just jump the gap. In both cases, the law of conservation of charge still has to apply. When I touch an object, okay, Andy was 10, I was 0, Andy touched my finger. I became +5, he became +5, total charge was still 10, right? When you rub two objects together, maybe one of them is neutral. Maybe they're both neutral. Okay, the balloon is neutral, your hair is neutral. You rub the balloon against your hair, the balloon becomes +5. What does your hair become? It doesn't balance. It was already balanced. What does it become? Total charge has to stay 0, right? If it was 0 before you rub them, it's got to be 0 after you rub them. One becomes +5, the other one has to become -5. Total charge has to remain the same. Can't create, can't destroy. Finally, last thing here, guys. Charging by induction. Two subcategories of induction. We're going to charge something. We're going to create a temporary separation of charge. We're going to create a permanent charge. So what do we mean by that? Well, let's draw a couple pictures. Let's say that I have a neutral object. Now, I've got the neutral object drawn as 3 positives and 3 negatives. It could be 16,124 positives, 16,124 negatives. It doesn't matter. It's equal number of protons and electrons. But let's bring a negatively charged object nearby. Doesn't mean that we have just electrons in that object. Okay, it just means that we have more electrons than protons. It's a negatively charged object. A couple quick questions here. First question. Mark, see if you know this one. What's going to happen to the protons in this neutral object as a result of this negatively charged object coming nearby? They're going to shift to the left. They're going to be repelled by the left. How many people agree with that? Anybody disagree? I disagree. Wait a sec. The protons aren't going to be pushed away? Cool. No? The protons aren't going anywhere. Why not? Because they're in the nucleus. And the nucleus is not going to give away its protons that easily. The protons stay where they are. Now, if you've got ions floating around in a gas, the positives can be pushed away. But if you've got protons in nuclei, okay, then the protons won't be pushed away. Protons are going to stay where they are. They want to be pushed away, they're going to stay where they are. What's going to happen to the electrons, Mark? Now you know this one, though. Yes, they're going to be repelled. Okay. The protons stay where they are. The electrons get repelled. Give you a trick question to start off. Second question, a little bit easier. The electrons get pushed over here. Not necessarily all of them. We're drawing it as if all of them they get pushed over there, but not necessarily all of them. But a preponderance of them get pushed over there. So that means that we got one side still neutral, 3 positives, 3 negatives, but one side of it is negative and one side of it is positive. Neutral object, but charges are separated. We've got a separation of charge. Why do we call it temporary? Why is it temporary? Yeah, good. Pull this guy away right here. Things are going to go back to the way they were more or less before you did that. Electrons are going to try to redistribute randomly throughout. It's a temporary separation of charge. Let's draw one more picture here. Let's say we got a neutral object again. 3 positives, 3 negatives, or whatever. 15,124 positives, 15,124 negatives. So I'm going to bring a positively charged object nearby. Not all protons, but more protons than electrons. Mark, what's going to happen to the protons? They're going to stay where they are. Good. What's going to happen to the electrons? Somebody else, I picked on Mark long enough here now. Josh? Yeah, they're going to be pulled towards it, right? These electrons are going to come over here. Not all of them, but lots of them. That leaves us, once again, with a neutral object, but the charges are separated. This time the left side is positive. This time the right side is negative. Now I want you to notice one thing here. First diagram, the side that's closest to the charging object is opposite to it. In the second diagram, the side that's closest to the charging object is opposite. Charged objects attract neutral objects, not because charge attracts neutral, but because positive attracts negative, because opposites attract. Whenever you have a neutral object and you bring something that's charged nearby it, you create a temporary separation of charge. That's why a neutron isn't attracted to a proton, because you can't get a temporary separation of charge in a neutron. There's nothing to separate. You have to have protons and electrons so that you can separate that charge so that opposite charges can attract each other. So that this positive can be attracted to that negative, and so that this negative can be attracted to that positive. Okay, these are still neutral, but there's a separation of charge which allows them to be attracted to the charging object. All right, good. One final little bit here. This is temporary, right? This is temporary. If I take this away, if I take the charging object away, in either diagram, they go back to the way they were before. The electrons spread out. How do you make it permanent? How do I make it permanent? How do I make it stay that way? Well, we attach what in North America we'd call a grounding wire, or in the UK we'd call it an earthing wire. You ever heard that term, earthing? A ground wire could literally be a wire that goes from the object into the earth, into the ground. But it could be any conductor that goes into any big object. Usually we think of it as the earth and a wire, but it could be you connecting the object to something else that's really, really big. Any conductor connecting it to something that's really, really big. What does that do? Well, now these electrons, in the first diagram, they were pushed to the left-hand side of the round object. They keep getting pushed. They can go further now. Instead of stopping there at the edge, they keep going down into the ground, literally into the earth, or whatever big object it is. That leaves me not with a separation of charge, negative and positive, but it leaves me with a positive object. But it's still temporary. One quick way to make it permanent now. What do you think it is? Yeah, go ahead. Yeah, cut the grounding wire, remove the ground wire. If you cut that ground wire before you take this thing away, then the electrons have no way of coming back. They want to come back, but they can't get back because there's no path for them to get back. A positively charged object. Almost the same deal down here. This time, however, the electrons aren't getting pushed down into the earth. The electrons are getting pulled up from the earth. Now you got a whole bunch of extra electrons in there. Now you don't have a separation of charge. Now you have a negatively charged object. How do you make it permanent? Cut the ground wire.